All right, thank you very much for having me here. Special thanks to the organizers. Today I'm going to discuss matching matroids over abelian groups, and this is a joint work with Shiraz Zerbi from Iowa State University. So this is the outline of my talk. It will have three parts. First, I will introduce a couple of notations concerning matroids. Then I will be discussing matchings in the group setting, and eventually the goal is to formulate matchings in the matroid setting and state a couple of results in this sense. So let's start with matroids. This is just a very traditional definition of matroid, which is roughly speaking a natural generalization of the concept of linear independence in vector spaces. So we are assuming that we are dealing with a pair. The first set is called the ground set, and I would be a collection of subsets of E. Elements of I will be called independent sets, and we have these three axioms. First, we contain the empty set. Second, every subset of an independent set must be independent. And the third axiom is the augmentation property. That is, when we are dealing with two independent sets, one smaller, one larger, then we can always extend a smaller one. And a couple of other terminologies. A set which is not independent is called dependent, and also a maximal independent set is called basis. Also, it is proved in matroid theory that, of course, two bases will have the same cardinalities. And also a circuit would be a minimal dependent set. I'm seeing a couple of questions here. Okay. Okay. Next one is the definition of the rank of matroid. So this is how we define rank over our matroid. The rank of each subset of the ground set would be maximal cardinality of the set with our independent set, and also we define the matroid of the rank of the entire matroid, which would be the rank of our ground set. And a flat is a subset with this property that adding every element to our set F will increase its rank strictly. And also hyperplane, we call a flat of rank of matroid -1 to be a hyperplane. And naturally, a circuit hyperplane would be a subset, which is circuit and a hyperplane simultaneously. And in this talk, we are mostly interested in three families or three classes of matroids: uniform matroids, paving matroids, and sparse paving matroids. So uniform matroids probably has the simplest structure of matroids. We are taking two non-negative integers. We take a ground set E of m elements, and we define a matroid of rank n as follows. Our collection of subsets would be all sets with at most n elements. And this is called a uniform matroid with ground set of cardinality m and rank n. And paving matroid, a matroid of rank n is called to be paving if all circuits are of size at least 10. It means every subset of rank cardinality n-1 must be independent. And also sparse paving matroid. What I'm mentioning here for sparse paving matroid, in most books. This is just a characterization, not the definition, but this is just easier to state this way. So I'm using it as the definition of a sparse matroid. A matroid of rank n is called a sparse Babing if every n subset is a basis or a circuit hyperplane. And roughly speaking, this means that every n set must be either a basis or must be very close to be a basis. And next, the next part of my talk would be about matchings. First, we are going to define matchings over abelian groups as follows. So we are assuming that G is an abelian group, and we are taking two finite subsets of G with the condition that they have the same cardinality, and the neutral element of the group is not in the second set B. Then a matching is nothing but a bijection F from A to B with this condition that for every element of A plus F of A is not an element of A. And matching property for groups is as follows. We say a group has the matching property if for every two finite non-empty subsets of the group with these two properties, same cardinality, B not having the neutral element, we secure the existence of at least one matching from A to B. And back to 1996, Fan and Loshanzi proved these two theorems. First one about matchings in groups in the symmetric situation, and second one in asymmetric situation. By symmetric, I mean these two finite sets A and B are identical, and asymmetric is the case when it is not symmetric. So when we are dealing with an abelian group and we take an empty finite subset A of it, then A is matched to itself if and only if A does not contain the neutral element. And regarding the matching property, we have this theorem that an abelian group possesses the matching property if and only if it is either torsion-free or cyclic of prime order. And in 2016, together with two collaborators, we settled the existence of matching for asymmetric case and for small enough subsets. So if we are dealing with two subsets A and B of an abelian group G, and their cardinality is less than the cardinality of the smallest non-zero subgroup of G, assuming that B does not have the neutral element, we can guarantee the existence of a matching from A to B, of course, in the group sense. So right now we have our collection of terminologies about Matroid. We understand how matching works. Next, we are going to discuss matchings in Matroid settings. But before doing that, it is worth mentioning that the concept of matchings has been generalized to vector subspaces in a field extension. And this is another attempt to generalize the previous setting, which is the vector space setting. So I'm not mentioning the existence, formulation, and results about vector spaces because of the time restriction, but we can start our definition in the matroid setting. So we are assuming that G is an abelian group. And first, we define matchability of matroids for the basis of matroids. When we are dealing with two matroids M and N of the same rank, assuming that this fancy M is a basis of the first matroid, this fancy N is the basis of a second matroid, we say the basis M is matched to basis N if we meet this condition AI plus BI is not an element of the ground set of the first matroid. And of course, here we are assuming that we are dealing with ordered bases. Next, the definition of matchings for matroids. So we are going to use the definition of matchings for bases to discuss the definition of matchings for matroids themselves. So we say a matroid M is matched to matroid N if every basis of the first matroid for every basis of the first matroid, there exists another basis of the second matroid, respectively called M and N. M is matched to N. And our first result concerning matching in matroids in the symmetric case. So dealing with a sparse paving matroid over an abelian group, then M is matched to itself if and only if the ground set of M does not contain the neutral element of the group. One reason here we are targeting sparse paving matroids is that this is a very important class of matroids, and it is conjectured and widely believed that asymptotically almost all matroids are sparse paving. Also, another conjecture back to 1960 with just very little progress is that almost all matroids are paving. So in the setting of sparse paving matroid for asymmetric situation, we have this theorem. So we are assuming that M is a matroid, N is a sparse paving matroid. Both of them have the rank N. And again, the ground set of our second matroid does not contain the neutral element. Under these conditions, we guarantee that M is matched to N. And what are these conditions? In all of them, pretty much, the size of ground set of the first matroid is less than or equal to the size of the ground set of the second matroid. And intuitively, this must be the case, because if the ground set of M is very large, then it would be difficult, if not impossible, to meet the condition of matchability in matroids. So in general, when the size of E of M is less than the size of E of N, then when this gap is relatively large, securing matchability is not very difficult, but the obstacles usually occur when their size is comparable. They are maybe this situation that they have the same size, or some other additive situations that we are seeing here. So, for example, when the ground set of our first matroid is a progression, again, it is difficult to secure matching from our first matroid to the second matroid. This is matchability in the setting of a sparse paving matroid. When it comes to uniform matroids, things are pretty straightforward, because every n set would be a basis, and every set of size less than or equal to n would be independent. So we can guarantee that, assuming that M is a matroid, N is a uniform matroid, and both of them have cardinality less than the smallest non-zero subgroup of our group G, then we can conclude that M must be matched to N. And regarding paving matroids, things become very complicated because in the sparse paving matroid, like I said, or in uniform matroids, every n set is a basis or very close to be basis. But in paving matroids, this is not the case much. So in this situation, we need to come up with some total ordering over our group. We are assuming that M is a matroid, N is a paving matroid, and they have the same cardinality n plus 1, less than P of G, which is defined previously. And we are assuming that we can define a total ordering on this set compatible with the group structure. I will specify what it means that we say it is compatible with group structure. And in this situation, with one minor extra condition, we can guarantee that M is matched to N. But again, let's get back to this total ordering that is compatible with group structure. So let's assume we are dealing with an abelian group. So we say a total order defined over group is compatible with this structure if for every 4 elements A, B, C, D of our group, A is less than C together with B is less than D will imply that A plus B is less than C plus D. The question here is that in what situations we can guarantee such a nice total ordering. It is proved in 1941 by Levy that in the abelian group, we have guarantees such a total ordering if and only if our abelian group is torsion-free. And in 2008, Lev proves this for a general abelian groups. If we are dealing with an abelian group and with non-trivial torsion subgroup, let's say of order P, assuming that a subset A of our group is small enough, this is small, it is less than the logarithm base of P, then we can define a total ordering over A, which is compatible with the group structure. And having these tools at hand, we can define like a positive set, a negative set in the group setting. And also we can define a nice total ordering over this subset of our group, assuming that this subset is small enough. Thank you. This was the end of my talk.